Hello. Today we're going to consider how we got from the Big Bang to the present day. In my series of videos on Hubble, Big Bang and the age of the universe, we derived the Hubble equation, V equals hd, where V is the relative velocity of galaxies moving away from us in the universe, h is Hubble's constant, and d is the distance between us and the receding galaxy. We concluded that since everything appears to be moving away from us, the universe must be expanding. If it is this size today, then it must have been smaller at some earlier time, and smaller still at yet some still earlier time. On that basis, working backwards, there must have been a time when the whole universe was just a point. That is what we call the Big Bang. We concluded that if Hubble's constant has remained constant throughout this expansion period, then the age of the universe is simply the inverse of Hubble's constant, which is 13.7 billion years. So let's consider what has happened in that period. At t equals 0, i.e. the time of the Big Bang, we have no idea what the universe was like. All the rules of physics break down at this point. There is no consensus. There are ideas about what it was like, but no proof. All we can really say is that the universe was infinitely hot, infinitely small, and infinitely dense. From that point to 10 to the minus 4 seconds, that is within the first 1/10,000th of a second, the universe expanded and cooled. It is thought that there might have been a single unified force which existed at the incredibly high temperatures of the Big Bang, but which soon broke up into separate forces which we know today. That is, the strong nuclear force, the weak nuclear force, gravity, and the electromagnetic force. The huge energy that was around meant that particles could be created according to the formula E equals mc squared, where E is the energy, m is the mass, and c is the speed of light. If you have a huge amount of energy, that can be converted to mass. The three main particle types were quarks, leptons, and photons. Quarks are the constituent parts of protons and neutrons, although there was far too much energy for their creation at that stage. Leptons are the family of particles which include electrons. Photons are the constituent particles of light. But for all the quarks and leptons that were produced, there would also be antimatter in the form of antiquarks and anti-leptons. Matter and antimatter should have been produced in equal amounts. There is also a suggestion that during this stage, the universe underwent a period of high inflation, where it expanded during a very short period super rapidly. At t equals 10 to the minus 4 seconds, the temperature was 10 to the 12 K, or 1 million degrees. Quarks formed into protons and neutrons. There are 3 quarks in each. A proton has 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. Matter and antimatter came together to annihilate, but the surprising point is that although there should have been an equal amount of each, which should have resulted in the total annihilation of all matter, a small excess of matter seems to have survived, which constitutes the universe we know today. However, the annihilation of most of the matter and antimatter would have produced huge energy in the form of photons. At t equals 100 seconds, that is 1 minute and 40 seconds after the Big Bang, the temperature was 10 to the 9 K. Conditions were star-like. Protons and neutrons could form helium nuclei. 300,000 years after the Big Bang, the temperature had cooled to 3,000 K. At this stage, electrons could combine with protons and helium nuclei to form the atoms of hydrogen and helium. Up to this point, photons had been continually scattering off the free electrons. Photons were continually giving their energy to electrons, which were then continually emitting fresh photons. This continuous interaction meant that light could not penetrate the universe, which was consequently opaque. Once the electrons were bound into atoms, the photons were free to travel through the universe, which then became transparent. Those photons, which resulted from the mass annihilation of matter and antimatter, are still constrained within the universe, since they have nowhere else to go, and we see them today, as we shall see later. Gravity is acting on hydrogen and helium atoms and pulling them together. This will eventually lead to the formation of stars and galaxies. 5 billion years ago, one of the stars that was created was our own sun. 4 billion years ago, the Earth was formed. That brings us to today. The universe has expanded still further, and as we know, the consequence of expansion is that the light is redshifted. That is what has happened to the photons that were created at the time when matter and antimatter annihilated. At that stage, they would have been extremely high energy, which means they would have had a very high frequency and a very low wavelength, probably in the gamma ray region. But now, with all the redshift as a consequence of the universe expansion, their wavelength has increased and their frequency decreased. The wavelength of those photons is now about 1 millimeter. They are microwaves. They form what is known as the cosmic microwave background radiation, CMBR. This radiation can be detected from all directions in space and is an indication of its presence throughout the universe. The average temperature of this radiation is an indicator of the average temperature of the entire universe, which is now 3 Kelvin. The cosmic microwave background radiation is surprisingly uniform, but with very tiny variations. Those variations are the reasons why galaxies were able to form in some places, whilst elsewhere in the universe there is empty space. What is the evidence for the Big Bang? Well, firstly, we have the evidence of the expanding universe, with a deduction that at some point in the past it must have been infinitely small, infinitely hot, and infinitely dense. Secondly, we have the cosmic microwave background radiation, which can be detected in all directions, and which fits nicely with the idea that this is the leftover consequence of matter and antimatter annihilation. Thirdly, the proportion of hydrogen and helium in the universe ties in nicely with the Big Bang theory. But can we know any more? Can we create the conditions at the Big Bang? Let us for a moment create an energy chart. We shall use a logarithmic scale, which means that each step in the chart will be 1,000 times bigger than the previous point. We start with a microelectron volt. An electron volt is a unit of energy which is equivalent to 1.6 times 10 to the minus 19 joules. If we increase by 1,000 for each succeeding point, we shall go up to a milli-electron volt, an electron volt, a kilo-electron volt, a mega-electron volt, a giga-electron volt, and a tera-electron volt, which is 10 to the 12 electron volts. Boltzmann demonstrated that temperature was essentially a measure of energy, and that energy measured in electron volts could be converted to temperature in degrees Kelvin by multiplying by 10 to the 4, which is a version of the Boltzmann constant. So for each of these energies, we can calculate its equivalent temperature from 10 to the minus 2 Kelvin to 10 to the 16. Where do the temperatures at the various stages of the universe formation fit into this chart? At 10 to the minus 4 seconds, the temperature was 10 to the 12 Kelvin. At 100 seconds, the temperature was 10 to the 9 Kelvin. After 300,000 years, the temperature was 3,000 Kelvin, and today the average temperature throughout the universe is 3 Kelvin. We can see from this chart that if we want to probe conditions at the beginning of time, we need energies of about a tera-electron volt. Happily, that is precisely the level of energy which can be generated by the Large Hadron Collider in Geneva. By smashing protons together at energies which are equivalent to those which were prevalent a merest fraction of an instant after the Big Bang, it is hoped that we will learn more about what was going on then.